All right, so basically we get into what I call discrete time and numeric solutions. Okay, so discrete time, have anybody heard that term before? What you okay, you're nodding.
Yeah.
Okay.
Discrete time.
What is it?
Well, we even discussed here. I think it's when you don't have something that is. Okay, I don't even know how to explain that. It's
So something that's not continuous,
yeah.
right? Okay. So when you have continuous time, basically what you're saying, like your time axis just goes forever. So like in the real world that we live in, like the time axis that we're living against goes, it's got infinite precision, is what I would say. Right? In other words, the timeline is real numbers. Right. So I can say that the time right now, I can define it with many, many digits of accuracy. In reality, a computer can't handle that. Right. So the computer has to have a way of dealing with that. So you guys are probably familiar with the terms analog and digital, right? That's a term that most people kind of just commonly know. What's analog and what's digital? Even though people know those terms, the question is, do they really know what they mean? What is it? So, and this digital means things are discrete in two ways. Um, Continuous time, or sort of analog, basically means that so if I'm measuring a voltage, and I say it's an analog voltage, that voltage is a real number, right? So any voltage that exists in the real world is a real number, right? At any given time, it is a number that has many, many decimal points, right? Or many, many digits after the decimal point. If I get that value into a computer, I can't handle that value, right? If the voltage is 1.00007632489 or something like that, I probably can't get that into a computer in a lot of cases. In other words, if I have a voltage that I'm measuring, so we're going to talk about this probably as we get into I guess the second project more so. Although we'll do it a little bit in the first project. If I have a digital signal, I have to basically convert that signal into a uh, if I have an analog signal in the real world, I have to convert it into a digital signal to be able to handle it. And usually that means that I have to use a certain number of bits to capture it. Okay. You guys have probably heard things like, 32-bit or 24-bit or whatever. We'll talk about what all that sort of means later. Usually we start by saying, well, what happens if we just take the time axis and convert the time axis into discrete steps? Okay. All right. So we're going to focus on that a little bit. All right. So, starting out just a little bit, just introduce this idea, right? So let's say I had this setup that I've got right here. So I've got an RC circuit. This is a simulation tool. You guys probably use different simulation tools like what do you guys use nowadays? Multisim. Okay, right. This is Simulink. It's a tool that I use a lot. Simulink is a MATLAB tool. Basically, I got an RC circuit. And what this does, you're not about to start using this, but I'm saying, okay, if I had a tool like Multisim or like Simulink here, if I have an RC circuit, and then what I'm doing in this RC circuit is I'm giving it basically a square wave of voltage. So voltage is going from 0 volts to 5 volts, and then back to 0, and then up to 5, and then back to 0, right? And this right here is the voltage V sub C across the capacitor that results from that. Okay. So if you've taken 2111 and you got all the way through that, you should be able to figure out what is this going to look like. If this input voltage is going from 0 to 5, all right, that's an exponential voltage on the capacitor. What would that voltage be if I solve the differential equation? So if I put a 5-volt step into that circuit, what's the voltage on the capacitor going to look like? Now, if you don't know the equation, what do you know is going to happen? I'm repeating it here, but if I look at it, basically, apply a step here, and it goes until this time, right? Then I apply the step down to 0. Imagine I didn't apply that step down to 0. I just let that guy go to steady state. What's the response look like? I get a steady state and a transient, right? If I put 5 volts into this circuit, what's the steady state response? 5. Okay. What's the transient response? Always. It's going to be an exponential, right? And it would be this, right? How do I know it's that? So I did negative t over tau. So first of all, we're gonna talk a little bit more about tau here, but anytime I have a first order differential equation, this particular circuit would give me, if I did the analysis on this circuit, I would get this. All right, this would be what the analysis would look like, right? So if I input voltage, that would be your differential equation. This thing right here is always tau, what I call tau. Okay, what is tau? If you know anything about, so I've used that term in the notes, right? But let's talk a little bit about what it means. What is tau? Tau's important. So if I solved this and I said, okay, if I just viewed this as a differential equation and I said, okay, you guys tell me how to solve that differential equation, right? And I said, give me the particular or the transient solution. I said, give me the transient solution to this equation. What would the transient solution to this equation be? How would I find that? That you should know how to do. So if I said this was my equation, how do I get the transient response? Set it equal to 0. And I guess, a e to the st or whatever. I'm going to end up with what I called that characteristic equation, right? What's the characteristic equation that's going to come out from this thing? Well, you got the right idea there, but that would be if it was second order, right? This is first order, right? So what would I get for a first order?
RCS.
You would get, RC times S plus 1 equals 0, right? If I did that the long way and I said plug in a e to the st, right? I plug in a e to the st, I take the derivative, there'd be an e to the st in each term. E to the st is never 0. So no matter whether it's first order, second order, third order, whatever, I always get the characteristic equation, right? It comes from guessing that a e to the st. So in this particular case, what I end up getting is that my S value is what? What's my S value here? Minus 1 over RC. All right. This thing, this RC, what I call this negative 1 over tau. Now we call that the time constant because what it does is it controls how fast the transient response goes away. All right. So if you've gone through circuits 1, how long do we say it takes for this transient to become 0? Usually we say about 5 time constants. Right. Now it's never gone, right? Because in reality, e to the negative t over tau is never going to be equal to 0, right? And only if I reach infinity is it ever 0. But basically we say it's pretty negligible by the time you get to about 5 time constants. In other words, by the time t equals 5 tau, this guy becomes e to the negative 5. And that's basically 0 at that point. All right, so that value of the time constant is important. All right, we're going to talk a little bit more about that. But if I solved this thing and I did it right, this would be the answer that I would get. Okay? 5 minus 5 e to the negative 2. Now let's see if it makes sense. What's the steady state solution? The steady state solution is 5 volts. So if I wait long enough, what happens to this? Goes to 0, right? So eventually this guy is going to become 5, right? And at t equal to 0, if the initial value of the voltage was 0, I would have 5 minus 5 times e to the 0. So the voltage on it would be 0, right? So that response should make sense. Okay. So what I want to do is I want to take a step back and say, all right, well, let's put that, in this case, let's say my tau value, just to give it a number, let's say my tau value is 0.1. So if we think that it takes 5 time constants for this thing to go away, all right, I want to figure out how I would sort of put this into MATLAB. So I want to think about, normally I tell you in MATLAB how to make your time vector and whatnot. But how should I make the time vector? We're going to talk about this a little more theoretically here in a second, but how should I make the time vector t? If I want to see this whole response, now you should know what this looks like. It goes like that, right? So the final value of it's 5, all right? So I want to draw that graph. How do I know to make the time vector? I'm going to start at 0. And if I want to see the entire thing, what should be my endpoint? If I want to see the entire transient response,
At least 5 times.
at least 5 time constants. So let's say I go to 5 tau. Okay. So if I was writing the code for this, I would say go to 5 times tau. And I would come up with some time step here to increment every time, right? I'd increment the time vector. So what value should I choose for that? What value should I choose for that? Just to be clear, tau is 0.1 seconds in my example. So that means I'm going to go from 0 to 0.5 seconds. Okay. So what should I do here?
I don't know, maybe over 1,000.
So basically, I should probably do something much, much smaller than tau. Right? So I'm going to take a number here. What did I choose in the code that I did? I'm going to do tau over 100. 1,000 would be fine. Right? 1,000 would be better. Smaller values are better. Okay. So in this case, I'm choosing small time steps. Now, in reality, this thing is a continuous function. Right? And so in reality, I should be choosing time values. I mean, I could choose time values that are basically real numbers. But how many real numbers exist between 0 and 5 or 0.5 seconds?
Infinite.
Infinite. Peter can't hold infinite, right? And so I got to choose some value that's going to be realistic. So I choose it knowing that that the time constant is really important. I choose a value that's smaller than the time constant. Because that sort of determines the features of what this thing looks like. So I know intuitively it's an exponential, and that its rise is controlled by this thing called the time constant. So basically, I choose a time step that is smaller than that time constant. So what I'm really doing is I'm making x into a vector of points. Okay. So what I'm going to do is I want to figure out, okay, well, how would I write the code to do this, right? And I want to relate this to the way I would write this code. So if I was in MATLAB, I'd say clear all. Start out like that. Okay. And one thing I guess I could do is I could write this guy out like so. I'm going to make a vector n, which is just integers. Okay. And I want to go from, how many points do I do? I'm going to make a vector of integers. What would that vector create? If I said, what does n look like? What would n look like if I made that vector right there? 0, colon 1, colon 600. What would that give me? Yeah, it would go basically in steps of 1. So it'd be 0, 1, 2, 3, 4, 5, 6, all the way up to 600. How many points would that be? How many numbers would that be? 601, right? Because I'm starting at 0. Okay. So it's 601 points. Now I'm going to define my tau value. I said my tau was equal to 0.1. So in MATLAB, okay, I couldn't say, I can't write, I don't have a Greek keyboard. So I would say tau equals 0.1, right? And let's say I'm going to make a variable called delta t, right? Delta t, so in that vector that I said I was trying to make previously, right? So it was going like this, 5 times tau. right? I'm going to define a delta t. Okay, so I write out delta t. Now, on the previous slide, I said my time step here was tau divided by 100. So how would I define delta t in my code? How would I write that? Tau divided by 100. Okay. Tau divided by 100. And I'll put a semicolon in there. Now what I want to do is I want to define my time vector, t. This is what I said my time vector is. Okay. I want to write that differently though. How can I use n and delta t to make that time vector? I'm going to use n and delta t. So the n vector I made, which is the vector of integers, and delta t. How can I use that to make that t vector? Multiply every value of n by delta t, right? What would that do? So if I multiply every value of n by delta t, so if n is, so I'm going to skip here where I actually have it written out. Let's see, right? So here's every value of n: 0, 1, 2, 3, 4, 5, so on and so forth. If I multiply, so I do t is equal to n times delta t, what are my t values going to be? Well, 0 times anything is 0, right? 1 times delta t. So in this particular case, what is my delta t? So tau was 0.1. Delta t was tau divided by 100. So my delta t is equal to 0.1 divided by 100 or 0.001. Okay. So when I multiply that vector of integers by delta t, what I get is 0.001, 0.002, 0.003, 0.004, right? So, I mean, it's not a particularly complicated thing to think about, right? I can use that now to make x. We've been doing that since the first homework, all right? I just did it a slightly different way. Now, the reason why I did that is I can think about this as another way as well, right? I can say this x of t that I wrote down here, if I really have my t vector not continuous, right? So in other words, continuous meaning it's real numbers. So there's infinitely many numbers between 0 and 0.5. In reality, it's finite numbers, right? I'm skipping basically every 0.001 seconds, right? So I'm only plotting it at 0, 0.001, 0.002, 0.003. Not really plotting this. I'm plotting an approximation of that when I draw that graph. So if I take that into account and say, well, what am I really doing? I can put in that n delta t here, right? Like that. Okay. Now, the way that I kind of think about this is the values of x of t that I get. So if I go through and plot those numbers, right? Those are the values that I'm putting into this thing for those different values of time. Those are the values that I get. Sometimes I don't look at it that way, though. Sometimes the way I look at this is I say, well, what I really want to know, if I'm thinking about what's in the computer, right? How does this sit in a computer? Once I actually code this, how does this sit in the computer? Right? Whereas in the computer, it doesn't think of it as a time vector, right? It's just a vector of numbers, it's just an array that sits in RAM somewhere, right? So it doesn't have any notion of there being time, right? So some level, I could think of this thing as x of n, right? So for n equal to 0, I would have 0. For n equal to 1, I would have whatever this value is, 0.049751, right? I can think of it that way, and I can think of this thing as a vector of points, right? So What would that look like if I graphed that? So I'm gonna come back to that slide here for a second. Here's what I'm showing. So I have my x of t there and my x of n here. Let's just take a look at what's the difference between these two graphs. Are they different?
One example number, one is the number.
All right, yeah. The key thing is when you look at this, you look at the y-axis values, they look the same, right? They're starting at 0, they're going up to 5, right? There's nothing going on there. The key difference is what's happening on the x-axis, right? For x of t, I start at 0. In this case, I end at 0.6, right? Because I actually did it for 6 tau. What am I doing here? What am I plotting? It's a sample number. This is going from 0 to 600. What's the difference?
You're plotting on n or?
I'm plotting on n, right? And I called it sample. Sample is the term we often use, which gets into the world of like analog to digital conversion, where I basically say, I sample something now, and then later, and then later. So in this case, I have samples. I basically pulled values off of the continuous function every 0.001 milliseconds. Or not 0.001 milliseconds. Delta t, in this case, was tau over 100, which is 0.001 seconds, or 1 millisecond. In other words, it's as if that voltage existed in the real world, like that. And what I did was I picked off values from that thing every millisecond. I said, what is it at t equal to 0? What is it at t equal to 1 millisecond? What is it at t equal to 2 milliseconds, 3 milliseconds? And what I did here is I basically said, well, just put those numbers in a computer. And then I can just say, if I have those numbers stored in an array in a computer and I just want to see what the numbers are, and I don't really care so much what the time is, I just want to see what those numbers are, I can look at it like this. This is how it exists in the computer. Up top is how you've placed meaning to it in the real world. But to the computer, it has no meaning. It's just numbers that sit in an array. That's what discrete time is, right? Is basically I just have numbers sitting in an array. And I can think of it as a function of n or as a function of time. It only has a function, it only has meaning in time if I can describe some kind of physical meaning to it based on the way I sampled it, all right? Now, all that stuff about sampling isn't all that particularly important for us just yet. What is, I think, hopefully a fairly simple idea is that the vector that I create is finite. It's got 600 points, 601 points, okay? And those 601 points sit in an array in memory. That's what I'm showing here, and that's what I'm showing there. I've just changed the time axis in the two cases. To get this one, what was the command that I did to make this graph here? I said plot what? Somebody other than you. What did I do to make this graph? If the vectors t, n, and x all exist in my code, what was the command that made this graph here? Somebody other than you. I appreciate your answers. I need some diversity. All right, he said it, t comma x, right? What do I do for this one? What did I do differently here? N comma x, right? Same graph, showing x both ways. I'm just changing what I'm plotting. All right, so in this concept of discrete time, I basically look at these things two ways. I say I have my continuous time functions, discrete time functions. They're related to each other. You can spend more time in signals and systems talking about the concept of discrete time. In reality, we deal with discrete time a heck of a lot more nowadays than continuous time. Because in reality, most things you guys deal with are digital, which means that you take a signal and you put it into a computer and you manipulate it in the computer. So as a result of that, discrete time is really important because anything that's digital is discretized, okay? If it's truly digital, it's not just discretized in time, it also has to be discretized on its y-axis as well, right? We're not touching that part, okay? We will have some of that in the project because if it exists in a computer, I can't store a real number in a computer, ever, right? because a real number has infinite precision. It has infinitely many decimal points or numbers after the decimal point, right? So I have to round things off in some way. So in any kind of digital system, there is some rounding that has to happen. Okay? So the big difference here is that I'm saying a discrete time function is only defined at certain distinct points in time. So it's a function of an integer variable n as opposed to a real variable t. Right? That's kind of the important point. All right. And discrete time represents how a continuous time function is studied in or stored in a computer memory. Okay. Now, the thing I want to think about for a second, back to my original question. You put that into a computer, multi-sim, right? You build that circuit. How does the computer solve that? Because computers have been solving those things since before they went to the moon, right? How do you solve? How would a computer solve to figure out this solution for a step function? Okay, numerically. So what's that mean? Some algorithm that would solve it, right? And so what would that algorithm be? Yeah.
Was that Newton's method or something like that?
Okay, yeah, there's a couple of methods. Newton's method is one of them, right? We're going to look at that one a little bit here in a second. But I just want to fundamentally, there's no way that the computer guesses a particular solution, right? What would that require? Well, that would require AI, right? I can't, in 1938, when they were trying to figure out how to launch missiles, they weren't doing AI to guess the solution to this thing. And, why did people build computers initially? They built computers to figure out how to fire rockets and how to fire missiles, right? So they were solving basically differential equations to figure out how to do that stuff. And there was no way to guess solutions and whatnot. So they had to come up with numerical approaches, right? And so what would be the numerical approach? And actually, the important thing about this to me is if I think about the numeric approach, it actually makes a lot more sense than it does to do calculus. Calculus feels old and out of date, right? In a lot of ways. The concepts of calculus are really important, but the specifics of it are kind of silly, right? Like in calculus 1 and 2 and 3 or whatever, you guys learned things like, I probably don't even remember. What's the derivative of tangent? What is the derivative of tangent? What is it? The secant? Something like that? Or secant squared? I don't even remember. It's kind of silly to go through that process of memorizing closed form solutions like that, because in reality, what really is important out of calculus to me are two things, right? Which is what? What's a derivative? What's an integral? What are those two things? What is a derivative and what's an integral? Well, yeah, so instantaneous slope, right? So if I'm talking about position, it's going to be a velocity. So the instantaneous slope of a function, that's important. That's what we're going to use here. All right. What's an integral? Area under a curve. Those are the most important things to know out of calculus. In reality, the computer can do the rest of it from there. All right. We need to understand that basically when I have a differential equation like this one, I need to find a way to take it to discrete time, understanding what this thing actually means, that it's the slope of a function at a point in time. Okay, so that means if I had a function here, y of t, all right, so this is the function in blue. Basically what Newton said is, well, I'll take the derivative, or the derivative is the slope of the function at that point. So you should have learned, well, if I draw a line basically tangent to that function at that point, the slope of that tangent line essentially is the derivative. Okay. So this gets us to what is the definition of a derivative. So dy by dt. What is, by definition, this is probably the important part. What is dy by dt? What is the definition of a derivative?
Instantaneous rate of change.
Instantaneous rate of change. And how do I write that mathematically? There's a limit here, right?
When delta t equals to 0.
All right. Basically, this delta t, so this step from t to t plus delta t, as that step gets really close to 0, it's basically what you learn for slope in algebra, right? Slope in algebra is what over what? Rise over run. So the run is delta t. So as I move delta t here on the x-axis, on the y-axis, how much do I move? Delta t, right? So I say y of t. There's a couple of ways to write it, but I'm going to write it this way. Y of t plus delta t minus y of t. So if I let delta t shrink closely down, that becomes what the derivative is. Okay. That's our basic approach to that. That is the definition of a derivative. This here is essentially just the slope calculation that you learned in algebra. And I'm saying I'm going to let the delta t, the run, get really small. Okay. So, all right, that's our definition of what this is. Now I want to use this in terms of a differential equation. So in the case of the computer, can I ever let delta t go to 0? No. But what can I do? I can make sure that delta t is small. And in particular, small enough. This is where the problems are going to come in for you on the project, for a lot of you. What is small enough? Well, small enough depends on the situation, right? What was my decision for small enough in this case? Right? When I did this, my definition for small enough was tau divided by 100. Right? How did I know that? Because I know that tau is the distinguishing feature of this. We're going to talk more about this later, right? But the tau of this thing is kind of the distinguishing feature in the time domain. I need to make sure that my decision for that time step is much smaller than that distinguishing feature, so I can capture all of the important stuff. So we'll look at that a little bit more. But if delta t is small enough, then basically I can say that dy by dt is approximately y of t plus delta t minus y of t all over delta t. If it's small enough, this approximation is good enough, as if it was a true equal sign, right? As long as my delta t is small enough, and again, small enough depends on the situation. We're going to spend a lot more time talking about what that means. All right, but if that's true, then this is true. And you should know, if I made delta t like a microsecond, that's probably small enough most of the time. All right. So I want to use that in this context. Let's say I've got a differential equation like this. So basically an RC circuit of some kind, I get a differential equation that looks like that. Tau times dy by dt plus y equals x of t. And I'm given some initial condition. I'm given that value, y of 0. All right. I always have to be given that value in differential equation to be able to solve it. Okay? If I'm given that, how would I approach this? How should I approach this? Well, we just said that dy by dt is approximately, using Newton's definition, that's approximately true. Let's say it was perfectly true. If that was perfectly true, how could I rewrite this expression right here? This is what I call discretizing it, converting it into discrete time. How could I change that right there? Using, let's say I make the assumption that this approximate is equal to exactly. That it was exactly, dy by dt was exactly that expression. That's the case, how can I rewrite this? Yeah, I would say tau times, I'd substitute this in, right? And I would say tau, and I'll do it slowly, y of t plus delta t minus y of t all over delta t plus y of t equals x of t. Like that. All right, now what I'm going to do is I'm going to rewrite this. This is an algebra expression, okay? it's an algebra expression because if I think about this, let's rearrange it a little bit, and then we'll think about why it's a simple algebra expression. What I'm going to do is I'm going to pull the delta t out. So I'm going to say that I have tau over delta t times y of t plus delta t minus y of t plus y of t equals x of t. What I want to do is I want to get this y of t plus delta t by itself. Okay, so how do I do that? How would I get that by itself? Well, I'm going to multiply both sides by what? What's my first step? Just algebra wise. I want to get y of t plus delta t by itself. What's my first step of algebra? Multiply both sides by what? Well, delta t over tau, right? Multiply both sides by delta t over tau. I'm going to get y of t plus delta t minus y of t plus delta t over tau, y of t equals delta t over tau times x of t. All right. Yeah, and then bring the y of t terms over. So I would get y of t plus delta t plus delta t equals delta t over tau times x of t plus y of t times 1 minus delta t over tau. Like that. All right. So I basically, what did I do? I brought this over, right? And then I brought this over. I had to subtract that from both sides to bring it over. Okay, so I end up with this. Now, let's just look at that for a second, all right? Essentially, so, and let me write it here. Let me say y of t plus delta t equals, what did I say? Delta t over tau times x of t plus 1 minus delta t over tau y of t, right? Yeah. All right. Now I know what y of 0 is. How would I use this in reality? How can I use this to solve the differential equation? All right. Well, anytime I'm given a differential equation, what am I going to know? Right? What do I know? I know what this input is, x of t. I have to know what that is to be able to solve it. I also have to know what the initial condition is. Right? So let's just say I have an example where x of t is equal to 1, right? And let's say that y of 0 is equal to, I don't know, 1 as well. Okay. How can I use that information to solve this thing? Right? How can I use that to solve this thing? Well, I could solve this at t equal to delta t, right? I could solve this at t equal to delta t, right? So how can I solve this for t equal to delta t? What value would I plug in for t in this? Let me be careful for a second. Let's say I want to solve for it at y equal to delta t. What I just wrote here, what value did I plug in just now for t? I plugged in 0, right? If I plug in 0, right, I have 0 plus delta t, I get that to be delta t. Right, so if I plug in t equal to 0 right here, what value would I plug in here? What value would I plug in here? T equal to 0 as well, right? So I would say this is delta t over tau times x of 0, right? What is this over here? And let's say, I know you guys don't like, let's assume delta t and tau were numbers for me. So let's say 0.1 and 0.001, right? Just those would be numbers that you would have. I know it starts looking weird when it's all variables like that, right? Let's say those are all numbers that I know. what would I have here? Well, 1 minus delta t over tau times y of 0. Okay. Given what I know here, what would do I know x of 0? And do I know y of 0? It's a differential equation. So what do I always have to know for a differential equation? I always have to know the initial condition. So I know that value, right? The input, I also know. So I'm going to get a number for y of delta t, right? That's going to basically say, knowing the values of the input and the output at time t equal to 0, I can find the value of that function at the next time step, right? What happens at t equal to delta t? Just going back to that expression. What would I be solving for there? If I plug in t equal to delta t, what would I be solving for? Yeah, the next step. So basically at time t equal to delta t, I would be solving for the value at delta t plus delta t or 2 delta t. Right? What value would I plug in here and here? I would plug in delta t over tau times x of 1, or x of 1, sorry, x of delta t plus 1 minus delta t over tau times y of delta t. Thing is, when I get to time t equal to delta t, do I know this value and do I know that value? I do, because I solved for those at the previous time step, right? So what it's saying is if I look at this, the value at the next time step of the output depends on the input, and it depends on the value of the output at the previous time step. That's the effect of the derivative kicking in. Yeah. That is called, it's called a forward Euler's method. Yeah. All right. So where'd you see that before? Okay. Good. You're good. Maybe you guys are more familiar with this than the differential equation. Yeah. Okay. That's good. Because the project will have a lot of this sort of stuff. Now, the thing you're going to have to do is in the homework, you don't have to do this. In the homework, I think I tell you what value to use for delta t. But in the project, you're going to have to think a little bit more about what is going to be the value of delta t, right? This is what I would call the forward Euler's method. Yeah. So it's, we don't need to, I don't worry too much about that detail. There's other methods that are more exact, all right, that you might have heard of, like Runge-Kutta. I don't know if they told you that. All right. This is a very simple, straightforward one. All right. We will only use this, yeah. All right. All right. Now, what I got from what I just did is that basically I get this. If the time right now is t, then the output at time t plus delta t depends on the input now and the output now. Okay. So what I just did on the previous slide, let's see, I came up with this result. Y of t plus delta t equals, what is it? Delta t over tau times x of t plus 1 minus delta t over tau times y of t. In the expression that I wrote here, what is A1 and what is A2? Because again, if I was writing code, you guys like to write code by just going straight to, you hard code things into code and then you go straight to things. I like to make it variable so I can see totally what's going on, right? Rather than hard coding stuff. What would I write for A1 and A2? Yep. 1 minus delta t over tau. Like that. All right. So I have those expressions. So basically the way that I look at this, all right, let's kind of go through for a second. I want to relate this into that discrete time idea, right? I want to relate this into the fact that my output y is just a vector of numbers. It only has a meaning in time if I give it a meaning in time. Okay. So think of it like this. So when t equals 0, so previously I had this thing I made a vector n, which went from 0 in steps of 1 up to 600. Okay. And my time vector, I said, was delta t times n. Okay. So that, if I think about what that's going to be, that's going to be 0. Let me just write it out. So it'd be 0, delta t, 2 delta t, so on and so forth, all the way up to 600 delta t. Right? That's what that vector would look like. That's what its entries would be. Okay? So at t equal to 0, n is equal to 0. At t equal to delta t, n is equal to 1. At 2 delta t, n is equal to 2. At 30 delta t, what is n equal to? 30. All right. So basically, the way I can look at this is I can say, I think of my y of t here. At t equal to 0, I'm solving for y of delta t. At n equal to 1, I'm solving for when t equals 0, I'm solving for y of delta t. At t equal to delta t, I'm solving for y of 2 delta t. What am I solving for at time t equal to 2 delta t? 3. Yeah. So I can think of this as, if I think of it just in terms of the values that are going to be in there, this would be the first value, right, that I would get. This would be the second value I would get. This would be the third value I would get, like that. Again, I'm saying those beginning at 0, so 0, 1, 2, right? So I should say y of 0, y of 1, y of 2, all right? So if I try to generalize this, right? So I can say, well, what do I get at time t equal to n delta t? And this should say actually n delta t. So basically I'm saying y of n plus 1 delta t equals a1 x of n delta t plus a2 y of n delta t. There's no particular reason for me to keep the delta t's in this. I can just say, how can I write this just in terms, how can I get the delta t's out of this? I can't, right? I can just say, can I just say that y of n plus 1, the next value of the vector, is equal to whatever x is now plus some combination of whatever y is now. This is basically the discrete time version of that statement, right? What am I saying? I'm saying the next value in the vector is related to the current value of the input and the current value of the output, right? Instead of keeping it in terms of time, I'll keep it that way because I'm just solving for values in a vector, okay? So let's use that in a real problem now. All right, let's use that in a real problem. So in this case, what do I have? All right, I've got that. And how did I do this? What did I choose for my, okay, delta t over 100. Okay. All right. So let's say I've got this guy right here. And what did I say for my y of 0? It was 10. Okay. Let's say y of 0, the initial value of the output is 10 volts. Okay. And I was told this. So in this case, my input is basically 4 u of t. So what does that mean, 4 u of t? That means it's 4 from when to when. When does it become 4? When does x become 4? If I have 4 u of t, when does x become 4?
0.
Yeah, at t greater than or equal to 0, right? So in other words, I can say this is 0.01 dy by dt plus y of t equal to 4 for t greater than or equal to 0. Okay. And the way that I would look at this here is, I've been talking in terms of tau here. So what's my tau value in this particular case? So the general form of these equations as I take them is going to be d tau dy by dt plus y of t equals x of t. What's tau in this case? Yeah, 0.01. And I'm going to choose a delta t in this particular case. And I'm going to say why I do that later. I'm going to say it's tau over 100. All right, so what would that be? That would be 0.0001. Okay, that would be my delta t. All right, so if that was the case, what I can do is say, all right, well, I use that Newton's rule definition, right? We said that I'm going to assume that y, the derivative dy by dt, is approximately equal to y of t plus delta t minus y of t over delta t. Okay. I plug that in to here as if it's completely true. Right? And I end up with 0, I'm gonna say it this way, tau times y of t plus delta t minus y of t all over delta t plus y of t equals 4. Like that. Okay. Now, if I go through the process of rearranging this, I can basically go back to what I had here, right? Where we defined, it looks like it's the same basic form as this thing, right? So I can basically go back to this result rather than going through all the algebra of those steps. I can say, well, basically it's going to be this. All right. So basically this guy is going to be, if I rearrange it, I'm going to solve for y of t plus delta t. And that's going to be equal to a1 x of t plus a2 y of t, where a1 and a2 are those two things I defined before. So a1 was delta t over tau, and a2 was 1 minus delta t over tau. Like that. Okay? So I have that sort of result. Now, what I also said was, if I think of this just as a vector of points in that discrete time version, I don't need to write everything in terms of tau. So if I do this in terms of n, how do I write this in terms of n? Y of what equals a1 x of what plus a2 y of what? What would I, if I wrote it just in terms not of time, but just assuming I had a vectors here, how do I write that? If I know the values at the given points, and I want to say the value at this point in the vector is related to the values at this point in the output vector, how do I write that in terms of just the values in the vector? Because again, when I go on a computer, y is just a set of numbers in an array somewhere. There's no time vector that's necessarily naturally sitting there with it. So I ascribe meaning to that physically. But in terms of the vector itself, what is this saying? The next value in y is related to the current value in x and the current value in y. So how do I write that in terms of this n, this integer vector?
Negative n delta t over tau.
Negative n delta t over, well, I'm not sure what you're, so in terms of the indices in the array, you would say the next value is related to the value now and the value now. All right, so in other words, the value at the next value in the y vector is related to the current value in the x vector and the current value in the y vector. Those two things are true if my t is equal to n delta t, like we've said. All right, so it's the t vector skips an integer number of delta t's every time step. Okay, so how would I use this to write? How would I code this? All right, so I'm gonna stop here. I'm gonna say, all right, what do I know? I know that y of n plus 1 equals A1 y of n plus, A1 x of n. And I know, let's see, move this out of the way, plus A2 y of n, like that. And I know that A1 is equal to delta t over tau, and that A2 is equal to 1 minus delta t over tau. Like that. Okay. And I have numbers for all those things. And I know that x of n, no matter what, x of n is equal to 4. And no matter what, y of 0 is equal to 10. And I have numbers for tau. Tau is equal to 0.001. And delta t is equal to tau divided by 100, or 0.0001. All right, so I know those things. How would I write the code for this then? How would I write the code to solve for y of n plus 1? Well, how would I do it for the first value? So x of n is 4, right? That was my input. And I know that the y of n is equal to 10, the initial condition, right? So let's just think about this. When n equals 0, y of 1 equals what? How would I code that? Well, I would say a1 times whatever x of n is. What's x of n? Well, it's 4, right? Plus a2 times y of 0. What was y of 0? It's 10. Okay. What's y of 2? That's when n equals 1. What's that going to be? A1 times x of n. X of n is always 4. Plus a2 times what? Y of 1. Now, where did I find y of 1? Well, previous. So what is this doing? This is basically, this is called an iteration, right? When I solve this, I'm solving it iteratively. I start out knowing the value I need, and then I basically jump to the next one using the previous one. So how would you write that in code? How would you do this piece here in code? With a for loop. All right, so I have y of n plus 1 equals a1 x of n x of n plus a2 y of n. All right, so I'm going to do a for loop. Let's say n, do it to make sure I'm consistent here. Go. I'm going to say for n equal 1 in steps of 1 up to, let's say I've already made my time vector somewhere. Okay, I'll come back to where why I ended there. All right, length of t minus 1. All right, come back to where I came up with that end, length of t minus 1. All right. How would I write this code to solve a for loop for this? Right? How would I do this? The way we say is the next value is always related to the previous value. Make sure I'm consistent. There's a couple of ways to do it. I could write this, couldn't I? I can just write in here y of n plus 1 is equal to a1 times x of n plus a2 y of n, and end the for loop like that. Okay. There's one catch to that. It's going to happen the first time I go into this thing.
We need to have an array that needs to be-
Well, I'm gonna need to have a Y vector that already exists, an array that already exists, right? That I will need to have. Okay, let's jump ahead to what I wrote here and see if you guys can follow, right? So this is what I wrote up. This is my A1. This is my A2. So let's just follow what I did here. So what did I do? Y underscore 0 equals 10. What is that there? What is that there? This here is my initial condition. Okay. I wrote in my tau, wrote in my delta t, and then I defined my A1 and A2. All right. So if you look at this expression here, right, that matches everything that I have. Then I defined a time vector. Okay. Now my time vector in this case, I basically took it from 0 to 7 tau. Why 7 tau? Well, because I decided 7 tau. 7 tau is going to be definitely after this thing is done, because we said it takes about 5 time constants for it to end. All right, then what did I do? What's happening here and here on those two lines? Y equals 0 size t, x equals 4 times 1 size t. What's going on there? Creating arrays. All right, so when I say y equals 0 size t, I'm creating an array of what? Array of zeros, and what's the size of it? Same size that t has. So what kind of vector is t here? Is that a row vector or a column vector? It's a row vector. So basically I have a single row vector, y, that has the same size as the time vector. Okay? And then what's the 4 times 1 size t? What's that going to do?
It's your act, and it's always 4.
It's always 4, right? It's got this, it's basically a vector of 4, right? It's a vector of 1s where I took every entry in the 1s vector and multiplied by 4. So it's a vector of 4s. It has the same size as the time vector. Okay. All right. Now in my for loop, what am I doing? Well, these two statements are basically the same, right? Right? Y of n plus 1 equals 5. Right? That is basically what this statement is. I just wrote that in there. What is this? It's my if statement. I got an if statement. Yeah, so if n equals 1, this is the thing that's confusing a little bit too, because I made an n vector that went from 0 to like something, like 0 to 700 in this case. In MATLAB, though, the first entry of an array is not the 0th entry. It's the first entry, the 1 entry. So what I said is the first entry in the y vector should be equal to the initial condition. I know that, right? There's this, in other words, this doesn't apply at that point in time because I'm solving for, think about it, at t equal to 0. So if I was solving for y of 0, that would depend on the value of x at when? Some negative time, and the value of y at some negative time. We're just told that before the input was applied, the initial condition was 10 volts, right? So we basically, the first entry is equal to the initial condition. And then everything thereafter solves for with this value. So I have that if statement there. So what's going to happen with this vector? Well, initially, y is a vector of zeros, right? The first time I go through this loop, so if I go through the for loop, n equals 1. What happens the first time when n equals 1? When I go through this for loop?
Y of 1 is initial.
The first entry becomes equal to 10. Right? So if after the first time I go through this loop, that happens. It executes that, then it gets to here. What's it do once it gets to here? It solves for what? Y of 2 using y of 1 and x of 1. What happens the second time I come through? Well, the second time I come through, n equals 2. So do I go into this if statement? No. I go to here. And I solve for y of what? 3. Next time, n equals 3. I don't go into here. I solve for y of 4. And I basically loop through this Why do I stop at length of t minus 1? What's that? Well, because essentially here I'm always solving for the next value. So when I get to the length minus 1, I'm solving for the value at the very last spot. Some of you are going to screw that up and you're going to go from 1 to 1 to length. And when you get to the end, you're going to be trying to shove a value into a place that doesn't exist. You're going to be trying to solve it at some entry after the end of the vector, right? So you'll run into problems with that. And remember, code always works. So it's just going to it's going to go through the for loop until it gets to the end, and it's going to, as you guys would say, MATLAB will yell at you, right? At that point, it'll be unhappy. All right, so what will it look like? This is what happens. What I plotted here on the top is the exact solution. So the exact solution meaning what I did if I go, here's the particular, here's the transient, solve by hand, all that stuff. I have plotted here the blue and the red, the exact solution and the one determined using this process. And what I did down here is I did the exact minus the approximate. Now what I see is this guy, you know, he goes from 10 to 0 to 4 volts, right? Which is what he should do if you figure out what you knew how to solve that different equation, and you should. He'd start at 10, he'd end at 4. This is the exact minus the approximate. Okay. They look, what does this tell me? Right? I plotted these together. Well, this tells me that there is some error. Right? Why does there have to be error? Because this is what approximation did I make that is making this error occur? The approximate is the solution I just got by doing this method. The numeric solution is always approximate, right? But it's really close, right? The difference apparently is about 0.011 is the maximum difference between the two. So they're pretty indistinguishable from each other. Why is there an error?
Because you assume that t is equal to its
right
limit definition.
Yeah, I basically got rid of the limit and just assumed, well, I probably made the delta t small enough, right? What happens if I make the delta t even smaller? Less error, right? I make the delta t smaller. So this was, yeah, tau divided by 100. That's tau divided by 10,000. All right. So if I look at this, the maximum error here was about 0.011. The maximum error here, MATLAB's deceptive. There's a 10 to the third up there. That means the maximum error is about 1.1 times 10 to the negative third. So it's an even smaller error, right? If I made it tau divided by 1,000,000, even smaller error. What's the downside, though, of making delta t smaller and smaller?
You work with more values.
It's my vectors are getting a lot bigger, right? So in this case, I had 700 points. In this case, I'm going to have 70,000 points, right? And I probably don't need 70,000 points if I think that error is okay, right? What happens if my delta t was bigger, right? Let's say I made my delta t, in this case, I made my delta t equal to tau, right? That's the real. This and this do not look alike, right? What it's saying is that by 0.01, so right here, it's saying that I feel like I've reached the final value, which is not at all true, right? That's the important point. So I got to make sure that I choose it properly. So if my delta t is too big, I get the wrong graph. My delta t is too small, it becomes a better graph, but maybe too much data for me to carry around on the computer. All right, and you're going to see that as we get into the project stuff. All right, so that's enough to be able to do that last problem on the homework. I will say this. If you look straight up at my formulas that I've done here, like this, what you're going to see is this came from a differential equation that was tau times dy by dt plus y of t equal to x of t. If you look at what I gave you in the homework, it's going to be something like this. I don't remember exactly how I did it. I don't remember what the exact numbers are. Maybe somebody has it handy. It's going to look something like this. That form and this form are not the same. What's the first thing you should do? You should convert this here into this form. How do I convert that? How do I do that? Divide by what? Divide by 4, right? Divide both sides by 4, and then it's in that form, All right, so that'll probably be something that'll cause a lot of you guys a problem. If I divide both sides by 4, it's in that form. Just my x of t becomes 1/4 of whatever I told you. Right, so basically the x of t that swallows up that 1/4. All right. Right. All right. You should be able to track that. All right. All right. I'll post this. I mean, the code that's here